Hello class, welcome to this video on probability statistics, chapter 2. We're going to go over the chapter 2 test, one of the versions of the test. So with that, we'll go ahead and get started. So we got the multiple choice here. Number 1, many professional schools require applicants to take a standardized test. Suppose that 1,000 students take such a test. Several weeks after the test, Pete receives his score report. He got a 63%, which placed him at the 73rd percentile. This means that, all right, so Pete got a 63%, but that placed him at the 73rd percentile. 73rd percentile means that 73% of people scored less than or equal to him. In other words, 73% of people did worse than him or equal to him as far as the score. All right, which means that Pete did better than 27% of them. Okay, so, did better than 73%. Sorry. So Pete did better than 73% of them, or 73% of them did less than or equal to him. Right. So in other words, like if X is at the 73rd percentile, then that means most of the data, that 73% of the data is less than or equal to X, right? Or X is greater than 73% of the data, right? If that makes any sense. So in this case, it says Pete did worse than or equal to about 63% of the test takers. No, that's just his score. That's not the percentile. Pete did worse than or equal to about 73% of the test takers. No, Pete didn't do worse than. Pete did better than, right? Pete did better than about 63%? No. So Pete did better than about 73%. So the answer is D. So 73% of test takers did worse than Pete, or you could say Pete did better than 73%. All right, so the density curve shown models the distribution of a quantitative variable that is equally likely to take any value from 0 to 2. What percent of the observations lie between 0.5 and 1.2? All right, so here we got between 0.5 and 1.2. So we're looking for the area of this curve, this part of the curve. So the area for that part of the curve is base times height, or length times width. The base is 0.7 because 1.2 minus 0.5. But let me just show my answer, show my work. And then times the height is 0.5, right? So in other words, it's 0.7 times 0.5, which is 0.35. And so the answer is 35%. All right, so now let's look at number 3. Which of the following is closest to the 28th percentile of the standard normal distribution? So if we got the standard normal distribution, we got to figure out what the z-score is so that the area on the left is 0.28000. As close to that as possible. So percentile is area to the left, recall. So we want 0.28000. So this is where we use the z table. We want the area to be 0.28000. So this is 0.29. Okay. So we got 0.28096, 0.27760. So this is pretty close to 0.28000, right? So let's choose this one. So it's going to be, so if that's the score, then we go here and here to figure out what the z-score is. So negative 0.5 for the z-score. And then let's go up here, negative 0.58-ish, right? So negative 0.58 would be approximately my z-score. Okay, so negative 0.58. Let's go back to the question. There you go. So then it looks like negative 0.58. That's closest to the 28th percentile. All right, number 4. For the normal distribution shown, the standard deviation is closest to what value? All right, remember the standard deviation is the point where you can identify the standard deviation is the point where you have the what we call an inflection point. So we know that this is the middle. And we know that, remember, it's the standard deviation is where the point of inflection is, meaning that the slope goes from really steep to not as steep. So if I were to say, let's just say we thought it was 4. Well, here, this is still pretty steep, and then it's steep there. So it can't be that point right there. But let's do the point 6. So if I do 6, well, then that's going to be over here. Now, this is going from really steep to right afterwards getting not as steep. Can you see that? So it's going from really steep to transitioning to less and less steep. That looks pretty good so far. Now, if you look at 8, the point 8, that's like over here. At this point, it already is very flat. Like the slope is not very steep there. Okay, so that's not going to be the inflection point here. The inflection point is going to be somewhere like halfway between the two peaks, essentially, because that's the point where it starts to transition from steep to less steep, somewhere halfway. And so this has got to be right around here. And if this is approximately where the inflection point is, or let's just say it might not actually be this point right here. It might actually be, this might be a little bit too short. It might be too small. We might actually need to go a little bit higher. So let's say 5 is over here. So 6 is actually, let me mark this with red. So if I do 6 is technically, right around there, right? That's 6. So that's a little too low because we want it to be somewhere like here, like halfway-ish, you know, between this peak and here, because then you can see, okay, well, it's going from really steep. Now this is pretty close, but it might be closer to 5. So if we go 5 and we're up here, 5 is going to be like around here, right? That seems to be the better point right there. On the curve. So 5, somewhere around here is what we're looking for the inflection point. 6 might be a little too high or too low on the curve. So in that case, it looks like 5 will be the closest to that. Okay, so therefore I would choose 5. So I would choose, if this is 5 right here, then that's like somewhere around here. This is approximately the point where, okay, it starts getting really steep and then it starts slowing down. This part is the part where it starts slowing down and then it starts getting really flat. Okay, so and with that in mind, if it's 5, then that means that the distance from here to here, that's my standard deviation. So what's the distance between 5 and 2? Well, so then that means sigma is 5 minus 2, which is 3. Okay, so the standard deviation is closest. It's not going to be exactly that. It may not be exactly that, but it's closest to 3. Okay, and if you did choose 6, right, because you thought, okay, it might be 6, then that's fine. That's fine, but then you would get a value of 4, and 4 is close to 3. Okay, so so you wouldn't choose anything else other than 3 in this multiple choice. All right, so there's number 4. So number 5, scores on the ACT college entrance exam can be modeled using a normal distribution with a mean of 21 and standard deviation 5. So we got mean is 21, we got standard deviation is 5, and Wayne's score, so that's his score, so that's the X value, his Z score, sorry. Standardized score, so Wayne's Z score is negative 0.6. What was his actual ACT score? So that's his X value. Okay, so remember the formula for X is mu plus Z sigma. So we can plug it in. We got 21 plus, we got the Z score is negative 0.6, and we got the sigma was 5. So we get 21 minus 3, which is 18. So his score is 18. All right, so the answer is D. Number 6, the Environmental Protection Agency, or EPA, requires that the exhaust from each motor of a motor vehicle be tested for the level of several pollutants. The level of oxides of nitrogen, NOx, in the exhaust of one light truck model was found to vary among individual trucks according to an approximately normal with a mean of 1.50 grams. There's your mean. and then the standard deviation of 0.25. Which of the following best estimates percent of light truck models of this level with levels greater than 2? So we're looking for x to be greater than 2. So that means that we have a normal distribution approximately where we have 1.50 in the middle, and then we're going by 0.25, so 1.75, 2.0, and then we got 2.25. And then on the left side, we got 1.25, 1.0, and 0.75, right? And they want to be the levels to be greater than 2. So that means we're over here. This is x is equal to 2. So if they want it to be greater than, it has to be to the right of that, right? And so this is an empirical rule problem. So you need to remember the magic numbers. So we got from here to here, this is 34. From there to there. From here to here is 13.5. And then from here to here is 2.35. From there to there, let me zoom in on that. And then from here to there is 0.15. So you can see that to get this red region, we had to add 2.35 plus 0.15. So we got 2.35 plus 0.15 is equal to 2.5%. So the answer is A. All right. Test number 6. Number 7, the figure shows a density curve that models the distribution of a quantitative variable. 7 values are marked on the density curve. Which of the following statements is true? The mean of the distribution is E. Okay, so this is skewed to the left, which means that the mean is more likely to be on the left, closer to the tail that is the longest rather than the peak. So it's not likely that E is the mean, because E is too close to the hump, the peak here. It has to be closer to the tail. So it's not A. The median of the distribution is C. The median is where you have 50% of the area to the left and to the right. This area does not appear to be the same size as this area. The area on the right appears to be a little bit larger than the area on the left. So it's not likely that C is the median, okay? The median might be actually closer, more on the right than it is on the left, okay? C is more likely to be maybe the mean or something like that than it is to be the median, even though it might not be the mean, but it's just a guess. The median of so it's not B. C, the third quartile of the distribution is D. Third quartile is where you have 75% on the left and 25% on the right. So if we got D, they're saying that this is like 75%-ish and 25%-ish. Is that really true? That means that 3 of these are going to need to fit into here. Is that really true? I don't think that's true. I don't think 3 of those on the right side fit on the left side. You would have to have literally 3 of those. So like 1, 2, 3, right? Of those. So it doesn't seem that that's true. I don't think that that's true. So I wouldn't say that. So I won't put C as an answer. The area under the curve between A and G is 1. Yeah, between A and G, the area in there has to be about 1. Yeah. So remember, that's the definition of a density curve, is that the area from under the entire curve is 1. So it's got to be D. All right, so number 8, a species of cockroach has weights that are approximately normally distributed with a mean of 50 grams. So we got mean is 50. Measuring the weights of them, a lab's assistant reports that 14% weigh more than 0.55 grams. So we got an area of 0.1400, converting that to decimal. And then we have a weight, that's my X value. That's my actual weight, so that's my X of 55 grams. Based on this report, what is the approximate standard deviation? So we are looking for that for this species. All right, so the formula for standard deviation is x minus mu divided by z. So we need to find the z-score. Now we're going to use this area to find the z-score. So if we know that this is a standard normal distribution, we want it says that 14% weigh more than. Okay, so let me put that is greater than 55. That means that whatever the z-score is, it has to be on the right. This is talking about the area on the right. It says more than. So more than, that has to be this right here. Since it's more than means area to the right, which means that the area to the left is 1 minus, right? So the area to the left is 1 minus 0.14, which is 0.86000. Okay, so we need to look up 0.8600 because that's the area that's given in the z-table. The z-table gives us the area to the left. And then we're going to use this to find the z-score. Okay, so let's go to the table, 0.860000. All right, so we got, this is really close to 0.86000, 85993. All right, so that means we're going to look further here and here to see what the z-scores are. Okay, so 1.08, 1.08. That has to be my z-score. So 1.08. That means this z-score is 1.08. All right, so now we got our z-score. So now we can calculate it. So we got x is 55 minus mu is 50 divided by 1.08. So we'll do the math here. I'll just do it on here. So 55 minus 50 is 5. 5 divided by 1.08 is 4.6-ish. Okay, so about 4.6. So the answer is A. Let me just put here 4.6 grams. All right, so in 1965, the mean price of a new car was $2,650 and a standard deviation was $1,000. Okay, so we got a mean and a standard deviation. In 2019, the mean was 36,700 and the standard deviation was 9,000. If a Ford Mustang cost $2,300 in 1965 and $34,000 in 2019, in which year was it more expensive relative to the other cars? So let's call this X1, X2. This is going to be mu1, sigma 2, well, sigma 1. This is going to be mu2, and that's going to be sigma 2. Okay, and we're going to plug those in. We're going to compare the two z-scores. We're going to calculate z-scores. Remember, z is the formula for z is all right here. Z is x minus mu divided by sigma, right? So we're going to plug that in. So z1 is equal to mu mu1 minus, or no, it's x1 minus mu1. So we got 2,300 minus 2,650 divided by 1,000. And then z2 is x2, which is 34,000 minus mu2 divided by sigma 2. All right, so let's calculate these two z-scores to see what we get. Okay, so I got negative 0.35. Do this one here. Get negative 0.30. All right, so those are our two z-scores. And then we want to compare which one is more expensive. So this one is less expensive because that number is less than this number. So z1 is less than z2, which means z2 is more expensive, slightly more expensive. So the $34,000 is more expensive, not because of the $34,000 price tag, but because relative to its mean price and standard deviation, it's pricier. Okay. So we're going to say 2019 is more expensive because the standardized score is greater than. Not because the $34,000 is greater than 2,300. It's not because of that. It's because of the standardized score. Because we're saying it's more expensive relative to other cars. All right. So number 10, the distribution of the time it takes for different people to solve a certain crossword puzzle is strongly skewed to the right with a mean of 30 minutes and a standard deviation of 15 minutes. So we got a mean. We got a standard deviation. Okay. It says the distribution of z-scores for those times is, so remember the formula for z-score is x minus mu divided by sigma. This is so it says the distribution is going to be what? So this is a transformation problem. Anytime you're converting from something to a z-score, the mean is always going to be 0, and the standard deviation is going to be 1 by 1s. So if you had a normal distribution, this is just an example, right, where the standard deviation is 15 and the mean is 45. If you convert that to z, you're going to have a normal distribution with a z-score with a mean of 0 and a standard deviation of 1. That's always going to be the case. Now, if you have something that's skewed to the left, right, and you have the mean is 30, and you got a standard deviation of 15, right, then when you convert this to z, it's going to still remain skewed to the left. So let me just draw it skewed to the left. However, the mean is now going to be just 0, and the standard deviation is going to be 1. Okay, so the only thing that changes is the shape stays the same, right? But the z-score, if you're converting it to z, it's still going to be 0 for the mean and 1 for the standard deviation. Okay, so the mean is still going to be that and that, right? So in this case, what we say is that, okay, so if it's it says it's strongly skewed to the left, right, or to the right, sorry, it says skewed to the right, so that means it looks like this, right, with a mean of 30 and a standard deviation of 15, so that means that's going to be go by 15s. Then when we convert this, it's going to still look the same, but it's still going to have the same shape, but the mean is going to be 0 and standard deviation is going to be 1. That's the value 1 right here. All right, so it's still going to be skewed to the right, but with a mean of 0, standard deviation 1. You just got to understand that concept. Once you understand that, it's really easy. Just the shape stays the same, but the mean is going to be 0, standard deviation is going to be 1. And that's really all there is to it. All right, so number 11, we're looking at the free response now. So for number 11, for more than a century, doctors have been telling patients that a normal body temperature is 37 degrees Celsius. There should have been a temperature here in Fahrenheit, so 98.1, right, or whatever, which is 37 Celsius. This value dates back to a study done by Carl Wunderlich in the mid-1800s. More recently, a researcher conducted a study to determine whether the accepted value is accurate. They collected body temperatures in Celsius from 130 individuals. All right, so we got 130 dots here. So that's and they say that here, 130 individuals. They give us the mean, standard deviation, all that stuff. Is this distribution approximately normal? Justify your answer based on the graph and the empirical result. So if I look at this, it kind of looks like it's approximately normal based on the shape, right? It may not be exact. It may be more skewed in one direction than another. Who knows? It might be skewed more to the right than it is to the left, but it appears approximately, but not exact. Which is fine. So based on the shape, it looks approximately normal, but we have to use the empirical rule test. It says justify your answer based on the graph and the empirical rule. The empirical rule, we're going to need to go 1 standard deviation out from the mean, 2 standard deviations out, and 3 standard deviations out to see if remember, for the empirical rule, the magic numbers are 68, 95, 99.7, right? So whenever I do this, it has to match these numbers. Okay, so let's look at first part. So the x bar, this is x bar. You have to know what that is. You have to know that this is S, right? So we got to plug those in. So we got 36.805 plus or minus 1 standard deviation. This is that, plus or minus 2 standard deviations. And then this, plus or minus 3 standard deviations. So we got to do the math. We got to do this plus that and this minus that, right? So let's just go ahead and say we did the math, right? And so you're going to get these numbers. And then you should verify this for yourself to see if you get the same numbers. So this is when I subtract, this is when I add. This is 0.584, and then this is 38.026. Okay, so now the hardest part is not in this part. The most annoying part is actually calculating the percent, right? So what we need to do is calculate the percent. What percent of people are between 36.3 and 37.2? Okay, now we got to be careful with the scale. So let's look at the scale real quick. It's going from 37 to 37.5, right? So that means there's an increase of 0.5, right? And there's how many spaces? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces. That means that each space has to be 0.5 divided by 10, which is 0.05. So each space is 0.05. So this right here is 37.05. Then this right here is 37.10, 37.15, 37.20, 37.25, 0.30, 0.35, 0.40, 0.45, 0.50. You see, that's 0.5 or 0.50. So each of those is 0.05. So we just keep that in mind. So we want to go from 36.398. So this is 36.0. This is 36.05, 10, 15, 20, 25. This is 36.25, 30, 35, and 40. So we want to go past 35, right? Because 398, right? That's close to 0.40. So we want to go basically to that point and on. And then 37.12, well, 37.12, this is 37.05, this is 37.10, and this is 37 point, yeah, we want to do 37.2-ish, right? So 05, 10, 15, 20, and then this is 37.25. So we want to basically go from here to the left, okay? Or, yeah, from there, because we want to go a little bit above 37.2, and then, so now we want to count these. We want to count these dots right there, okay? So let's go and count them real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 57 so far. That's 78, 9, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95. It's actually, this is right here 30, this is 0.30, this is 0.35, and this here is 0.40. Okay, so yeah, I have to include this as well. So let me just make sure I do that. So I want to include this onward. I forgot to include those two dots there. Okay, so that means I have to include these as well. All right, so there's a total of 97. Okay, so there's a total of 97 from that right there. Okay, so that's 97. All right, so 97 observations between there and there. So 97 out of 130. And we multiply that by 100 and we get about 74.6%. So about 75%. All right. And then let's look at the observations. Now we got to go from 35.991 to 37.619. So 35.991. Do this in red. So that's pretty close to 36, right? 35.991. So this is right here, 35.75. Then we got, so right here, this is 36.0. This is 35.95. Okay, that's what that is. And we want it from 9.9 and on. So we don't want 9.5. So essentially we want from 36.0 and on, right? And then we want all the way up to 37.6 and a little bit after the 6, okay? So 37.6, this is 37.5, 37.55, 37.6, right? So we want, and then this is like 6.5. So basically we want from here on, so we don't want to include that dot there. So we want to include this as, so we want to include this part, and then we want to include that part, okay? As well as the black part. Okay, so this part right here is 1, 2, so we got 97, so 98, 99, 100, 101, 2, 3, 4, 5, 6, 7, 8. So that's 108, 9, 10, 11, 111, 12, 13, 14, 15, 16, 17, 18, 19, 120, 21, 22, 23. So about 123. Yeah, so then in that case, it's about 123 if I add the red and the black parts. So we got about 123 then. So let's see. So let's go over there then. So we got 123. So that's about 94.6%. That's close to 95. All right, so then 35.58 and 38.02. Now 35.58, that's really close to that. So that's like right around there. So basically all of that. And then 38.026, 38.02. This is 38.05 right here. So it's basically from here on. So we don't include this last dot. So basically all the dots, all of the data except for the last dot. So that's 129. Okay, so we got 129. Out of 130. So that's 99.2%. Okay, so again, we got to compare that to the 68, 95, 99.7 rule. Now 99.2 compared to 99.7 is pretty good. 94.6 compared to 95 is pretty good. But the only part is the 74. The 74 is a little bit off. In fact, it's a little bit too off. It's about 6, almost 7% off. So that's really what's preventing it from being close to being approximately normal. So if you say that that's close enough, I will give you credit. If you say that it's supporting work, that you show, okay, this is close enough to 68, even though it's pretty off, I will still give you credit. If you said it was not normal because it was too far off from this number, that's really what I'm leaning towards, is that this was far, it's a little bit too far off for the first number. Okay, so the shape appears to be approximately normal, or appears to be bell shaped. But the empirical rule test indicates that it might not be approximately normal. since 74.6% is a bit far off 68%. Now, if you said that it's close enough to 68%, we could say it, then that's fine, because it's sort of like a weird valley in between, where it might be considered, if you put a cutoff, it might be a little bit. Now, if it was 10% off, then probably not going to be close enough. This one is like 6-ish, 7%, right? So it's sort of like in between, but I would say it's a little bit too far off. All right, so number 12. According to the TrueCar.com website, and the asking prices for cars of a certain model are approximately normal, with a mean of 35,987, standard deviation 607.50. Draw and label the normal distribution. Label the percentages using the empirical rule. All right, so we got a mean here, 35,987, and we're adding the sigma here, and we're subtracting the sigma there, right? And we're using these lines as our guidelines. Okay, so if I add 607 there, 50, I'm going to add $607.50 to that, and then I'm going to subtract it. Okay, so let's do that. So if I do that, I get $35,594.50. For the next one, I get $37,202. This one I get $37,809.50. And then we gotta label this. This is the car asking price in dollars. This is $35,379.50. I got to keep subtracting $607.50, so I get $34,772, and then the last one, $38,168.50. All right, so those are my x-axis labeled with the title here. And we have to label the percentages using the empirical rule. So this is 34%. This is 13.5%, this percentage here underneath the graph. And we got, this is 2.35. And then the last one is 0.15%. Okay, so there you go. So that's part A. That's what it's asking for. Now, part B, about what percent of cars have asking prices below $36,594? Let's see. Oh, this should say 36,000, not 35,000. Right here, that should say 36,000, not 35. Okay, so so we below that price. So we're gonna go, okay, so this is the price that they're talking about. They want it to be below. So really we're doing the area to the left, right? And so we need to add up all of these percentages, 1, 2, 3, 4, 5. Okay, so we're gonna add 0.15 plus 2.35 plus 13.5 plus 234s. So if I add that, I get 81.5%, or no, about 83%. Okay, so 83% of cars have asking prices below that. Okay, that's it. So that's number 12. Number 13, it says bigger animals tend to carry their young longer before birth. The length of horse pregnancies from conception to birth varies according to a roughly normal distribution with a mean of 336 days and a standard deviation of 6 days. Sketch the normal curve that models the distribution of horse pregnancy length. Label the mean and the points 1, 2, and 3 standard deviations. So this one's a give me point. This one's an easy one. You just got to label just like we did in number 12. Okay, so just draw a normal distribution and label the, label your stuff. We got horse pregnancy term in days. We got 336 is in the middle because that was the mean, right? And this is a standard deviation 6, so you're going to go by 6s. So then the next one's going to be 342, 248, 354. Then you got to subtract 6, so 330, 324, and then 318. And that's all we're looking for part A. So easy point. What percentage of horse pregnancies are less than 340? So now we're looking for less than 340. So 340 is like here. So we're looking for the area to the left of that, right? For part B. So now, because it has to be less than, we need to convert the 340 to a z-score. So we're going to say, okay, x is this is x, 340. So let z is equal to x minus mu divided by sigma, right? The x is 340. The mu is 336. And then the sigma was 6, right? So we're going to calculate the z-score. The z-score is about 0.67. All right, and then we need to look this z-score up on the z-table. So let's do that real quick. So 0.67. 0.67, and then we need to figure out what the value is from that. So the value is 0.74857. 0.74857. So that's the area on the left. That's that area right there. And it's area to the left, and that's what we wanted. So there's our answer. Okay, so the probability that z is less than 0.67, we got an answer of 0.74857, which if you convert to a percent is going to be 74.857%. All right, what percent of horse pregnancies are greater than? So now it's going to be greater than 350. So if 350, this is not 340. 340 is like over here. I don't know why I put 340 there. That's fine. I used the wrong marker on there, but it doesn't matter. All right, so as far as the answer. All right, so now we got greater than 350. So 350 is like here. We want it to be greater, so we want the area to the right, okay? So again, convert that to a z-score. 350 minus mu divided by sigma. So we got 2.33 for the z-score. We're going to look this up. Remember that since we want the area to the right, we look up the z-table, and then we subtract from 1. We do 1 minus that. The z-table always gives us the area to the left. All right, so let's look up 2.33 on the z-table. Remember that the z-table always gives you the area, let's see, it says here, it always gives you the area to the left, all right? So keep that in mind. All right, so we got 2.33, so it's gotta be 0.9910, 0.9910, but that's the area to the left, remember. 0.9910. So since that's the area to the left, we have to do 1 minus that, okay? So the probability that z is greater than 2.33 is 1 minus the probability that it's less than. The less than is from the table. So 1 minus the table value. Table value was 0.99010. So just do 1 minus the table and you'll be fine. 0.00990, which is 0.99%. There's a decimal right there. 0.99. All right, so how many days would a horse pregnancy last for it to be at the 35th percentile? So we want 35th percentile. That means the area to the left has to be 35000. All right, so we need to look this up. The area from the table is 350,000. We need to convert this to a z-score. Right, so we're going to look this as 350,000 on the z table and look for the z-score. Okay, so let's look that up. So we want an area of 0.35000, not a z-score, an area of 35000. So these are the areas. That's 34458. That's pretty close. We want it even closer. If possible. I guess that one might be the best value. It might be. Let me see. 3500. Oh, that's pretty close to 35. Yeah, so it's between this and this, but this is farther away. So I'm not going to choose that one. This one seems to be the closest to 3500. It's between that and this one, but this one's slightly closer. But you can choose either one. So either this one or this one. So let's just choose this one. So then the z-score has to be, gotta look that up from there, left and up. The z-score is -0.3, -0.39. Okay, so -0.39. All right, so let's go back. So -3.9 seems to be my z-score. All right, -0.39. Okay, so this is approximately -0.39. And now how many days? So they're looking for x. So this is an x equation. So x equals mu plus z sigma. The mean is 336 days for the horse pregnancy. The z we found just now. The sigma they told us was 6 days for the pregnancy, for the standard deviation. And we do the math. We get about 333.66 days. All right, that takes care of that one. So we're wrapping this up here shortly. So we got a couple more questions. Number 4, fast food restaurant has just installed a new automatic ketchup dispenser for use in preparing its burgers. The amount of ketchup dispensed by the machine follows an approximately normal distribution with a mean of 1.1 fluid ounces. So the mean is 1.1. What should the standard deviation be? So a question mark. To ensure that 70% of its burgers have at least, that means greater than or equal to, 0.8 ounces of ketchup. This is my X value. So we have the X value, we have that it's 70%, we have that it's greater than or equal to, which means we're looking at the area to the right. So in other words, we have, this is the rough sketch. We have approximately normal distribution, 1.1 in the middle. We have 0.8 ounces for the ketchup that they're looking for. And we have that 70% of the burgers are at least that much ketchup. So that means greater than or equal to. So this is 70% or 0.7000. Now the table gives us the area to the left, which means we need to look up 0.3000, right? 1 minus 30% on the left, 70% on the right. The table only gives us the area to the left, so we need to look up 30%. So let's look up 30%, and that will give us a z-score, because we don't know what z is. So let's look that up, 30%. All right, so 30%, those are big numbers. We need to go to the smaller numbers. So this one's 35%, so it's going to be closer to this area. Let's go to 30, though. So 30%. That's 28%. Okay, right here, 30%, 30%. This looks pretty close. Okay, so yeah, this looks pretty close to 30%. So we're going to pick that one. So then the z-score is negative 0.5, negative 0.52. Okay. All right, so negative 0.52. Let's go back. Okay, that was the horse pregnancy. Okay, here we go. So the z-score. All right, so z-score is approximately negative 0.52. So now we can calculate the sigma, okay? So sigma equals x minus mu divided by z. We just found the z-score. We know x, we know mu. We can plug it in, okay? X is the 0.8 ounces. All right, so we got 0.8 ounces minus mean is 1.1 divided by the z is negative 0.52. Plug that in, we get about 0.58 ounces. All right, that's what my standard deviation has to be. All right, and then the last question, number 15. Find the probability that z, or the percentage or proportion, that z is between negative 1.52 and 0.67. Sketch, label, and shade the standard normal distribution. So again, that's part of the question. So we're gonna draw the standard normal distribution. That's z. So 0, 1, 2, 3, negative 1, negative 2, negative 3. And we're going to sketch, label, and shade. So negative 1.52 is here, and 0.67 is here. So we just want to shade this area right here between those two. So what we got to do is look these two values up on the z table and subtract the values from the z table, okay? So in order to find this, we need to do the probability that z is less than 0.67 minus the probability that z is less than negative 1.52. So we got to look at the 0.67, look at the negative 1.52 from the z table, subtract them. And that's it. That's all there is to it. All right, so let's look this up. 0.67. Gotta go back to the z table, go back up here. So 0.67. So 74857. And then let's go look up negative 1.52. Negative 1.52. So 0.06429. So subtract those two numbers and get our answer. Let's do that. Yeah, here we go. So first number was 74857 minus 0.06429. We get 0.68431. Well, that's it. That's all there is to it. That's going to do it for the video, guys. Hope you found this useful and informative. And as usual, I'll see you in the next one.